Hey, good morning, everyone. Looks like we had a little technical snafu. We're just going to start from the beginning of David's thing. You don't need to hear my bit, so sorry about that. We didn't click the little start button. So I guess I'll just introduce it real quick again. Welcome to the 20-minute webinar with Rath Associates. This week, we're going to be talking about new pumping technologies old designers should know about. So without further ado, I'm going to pass it off to David so we don't go too far beyond our 20-minute time frame. So sorry about that, and sorry, David. Why don't you just take another quick start at this?
All right, sure thing. Thanks, Greg. And good morning, everyone. Here's our agenda for today. We're going to start with an overview of today's HVAC pumping landscape, and then we'll jump into our three main topics of interest: sensorless pump control, parallel pumping systems, and redundancy. And then we'll be looking at the new technology in the permanent magnet motors and how we can use higher operating speeds to our benefit. So some of the issues that we see today in today's industry as far as traditional pumping systems are that there's not much data on the system, and there's not a whole lot of corrective actions that we can take as far as correcting what's happening in the system. So, for example, we see a lot of pumps being left in deadhead or left running in hand mode. And we also hear about the issues with pressure sensors. So many times there are many installation problems. We have to knock out walls or wire them from the top floor all the way back down to the basement mechanical room. Sometimes the mechanical room is not in the same building, so the pressure sensor has to be wired across a parking lot. And because of all these issues, the pressure sensor may not be able to be installed at the most remote load, and we end up installing it back in the mechanical room and not able to meet ASHRAE 90.1. We also see a lot of pumps selected for duty standby configuration, which leads to excessive redundancy. And this also leads to oversized pumps and motors, as well as the wall-mounted VFDs, which take up a lot more space and increase our installation costs. So what our design envelope solutions do is that they provide the lowest first cost and lowest life costs. And all of our design envelope pumps today are now able to be connected to the cloud for optimization via machine learning. We won't talk about that in today's session, but we also have the sensorless pump control, which is essentially a control algorithm that's embedded in our pumps that allows you to eliminate the use of a DP sensor. We also include appropriate redundancy using our parallel pumping, and this will allow us to reduce equipment and installation costs. So sensorless pump control, as I said, is a control logic that simulates a single zone differential pressure sensor operation. This is a logic that's fully embedded into the controls, so we are able to eliminate the DP sensor. We're also able to eliminate the wiring, locating and installing any sensor, and setting up of the range. And all of the calibration and drift issues are also eliminated. The big benefit of sensorless pump control is that it's all pre-programmed, mapped, and tested at the Armstrong factory. So there's no on-site custom programming required by the controls contractor. He doesn't have to do any validation or any UL testing either. And this leads to a $2,000 savings on the cost of the sensor and installation. So how exactly does sensorless control work? We've got a slide here showing control with a sensor versus sensorless control. So in a sensored control system, you have your cooling coil or heating coil with a control valve on the end there, and that's connected to a DP sensor. So as that control valve starts to open and close based on the demand in the system, the changes in the system are read by that DP sensor, and then that provides a signal to the VFD as a 4 to 20 milliamp. And that the VFD will read that signal and it will modulate its speed according to what it reads from the DP. The sensorless control system actually works very similar to that censored control system. However, the changes in the system are interpreted as motor amp draw change. So we've got our control valve here opening and closing, and what the design envelope pump does is it compares its amp draw to the sensorless program map. So as the control valve were to start to close, normally the pump will try to ride up its pump curve, but the DE pump will see that the sensorless map doesn't match what it was programmed for, and it will slow down to get itself back onto its control curve. Conversely, if that control valve were to start to open, it will try to ride out to the right of the pump curve, but see that it doesn't match what it was programmed for, and it will speed up to get itself back up onto the control curve. So it's always looking for that constant feedback to adjust itself to the system conditions. Now looking at parallel pumping systems and redundancy, we often see two pumps installed side by side like you have in the photo here, but only one pump ever operates at a time. The other pump is just there as a standby pump in the event that you need to do maintenance or in the event of failure. And many installations will have an alternating schedule for equal wear on the pumps, but rarely do you ever see the two pumps operating at the same time. So it's really a overly redundant system. So why would we want to use parallel pumping systems? And that's mainly because HVAC pumping is usually operating in part load. So we can actually select multiple smaller pumps to economically handle that load. And if one pump were to fail, we still have sufficient redundancy for the remaining pumps to handle that load. Unlike other equipment like boilers or chillers, the system redundancy is not directly determined by the number of pumps. And what I mean by that is, if you had two boilers or two chillers, for example, if you lost one chiller, you'd be down to 50% redundancy. That's not the case with pumps because of the shape of the pump curve. You actually get a little bit more than that, and I'll explain that in the coming slides. Here are some of the benefits to using parallel operation. So mainly we're able to reduce capital costs if we're going to smaller equipment. And so the approach here is to take, for example, if you needed a 1,000 GPM flow rate at design day capacity, we split that up into a 500 GPM pump and another 500 GPM pump, and we run the two in parallel to get our full design day capacity. And the reason that works is because of the pumping system being part load, we don't always need that full capacity. We're also able to reduce our energy costs. So I'll talk about our parallel sensorless pump control, which uses best efficiency staging, which allows you to reduce the energy costs. And ultimately, when you're going to smaller equipment, you're able to reduce your space as well as your footprint. So here's an example of our reduced installation costs. In the photo here, you see a traditional duty standby base-mounted horizontal system. We've got the DP sensor somewhere out in the system with the wiring all the way back to the VFDs in the mechanical room. If we go to vertical inline configuration, we are able to eliminate the flex connectors and the inertia bases, as well as the housekeeping pads. So there's a installation cost savings there. Also with the sensorless control here, we're able to eliminate the DP sensor, the $2,000 savings that I talked about earlier. And if we go further to our dual pump configuration, which is our Tango or dual arm pumps available from Armstrong, these are essentially two pump heads in a single shared casing. We're also able to eliminate one set of suction guide and triple duty valves, as well as one set of piping risers for an even further reduced installation cost, as well as the smallest footprint possible. And this type of configuration is actually very popular with chiller manufacturers. They like to have these very compact dual pumps that provide the extra redundancy and install them in their OEM packages. Here's an example of the sizing. Two 20 horsepower pumps sized for 100% duty standby versus two 10 horsepower pumps sized for 50% operation in parallel. And here's some of the number figures of the savings. And if you look at the criteria for pump weight, installation footprint, and installed cost, you can see over on the right there are installed cost savings and pump weight savings all exceed 65%. Now, flow redundancy is a term that's simply defined as the flow rate when one pump goes down relative to the design day flow rate. So here's an example of how the capacity split, if you split the pump flow rate by 50-50, how that results in more than 50% flow redundancy. In fact, you actually get 70% flow redundancy. So what we have here is a two pump curve as shown in the gray. and our system curve here in the blue. If you were to lose the second pump, you still have the one pump in red intersecting with your system curve. And because of the intelligent variable speed controls, we're still able to speed up to give us additional flow rate. So in most cases, you're going to get more than 70% of flow redundancy, even if one pump fails in a two-pump system. So if we take advantage of that and look at it in summary, if you size a two-pump system for 2 times 50% capacity split, you would get 70% flow redundancy and 90% heat transfer to the cooling coil. If you sized it for 2 times 70% capacity, you would get 85% flow redundancy or 95% heat transfer. And if you size it for 100%, you still get 100 and 100 heat transfer to the cooling coil. So we chose to show the heat transfer to the cooling coil because the heat transfer to a heating coil is actually much easier to achieve. That would be 95, 98, and 100%. But as you can see, there's not much impact as far as occupant comfort. Even for a 70% capacity split, you still end up with 95% heat transfer. So looking at that and looking at the types of buildings that we want to size this for, we recommend for 70% flow redundancy that be used for schools, apartments, factories, and warehouses and condominiums. If we're looking at high comfort sensitivity applications, such as your hotels, offices, commercial buildings, and universities and college campuses, we recommend an 85% flow redundancy or the 70-70 capacity split. And then for our mission critical applications, such as our hospitals and data centers and blood banks, we recommend that those be maintained at 100% flow redundancy. So our Armstrong's Sensorless pump control is another embedded control logic that stages multiple pumps up to 4 pumps for best efficiency operation. Again, this logic is fully embedded into our controls, so no external PLC or controllers needed. You're also able to eliminate the DP sensor out in the system. So a lot of those issues with installation and energy drift issues are also eliminated. These are also pre-programmed, mapped, and tested at the factory. So a duplex control panel or any sort of triplex or fancy control panel from a controls contractor with the programming and on-site testing, that's also eliminated. And as a benefit, we provide the standard on all of our dual pumps, our Tango and dual arm pumps, and we offer it as an adder for our single vertical inline or end suction pumps if you were to order multiple pumps and wanted to run those in parallel. And this is how the best efficiency staging works and how it reduces the operating cost. So on the top, we're showing best efficiency staging compared to speed-based staging. And we've got our pump curve here with our control curve in blue, shown on both the top and the bottom. And we've got the pump efficiencies for pump 1, pump 2, and pump 3 shown on the top in the red. So as the control valve starts to open and we start to get more flow, we would operate normally both pumps. We still operate the first pump up until a point where it becomes more efficient to stage on the second pump. However, in the speed-based approach, you would still continue to run the first pump up to about 90% speed before you would start to stage on the second pump. So here we're operating at a very efficient point for the second pump, and we're consuming only 20% power compared to 30% power with just the one pump. And this is even more pronounced when you go to the 2 and 3 pump because of the shape of the efficiency curves here. Now we're staging on the third pump, whereas with speed-based staging, we've only got the 2 pumps running, and we're consuming 75% power compared to only 40% power. And while this sounds a little bit counterintuitive, typically you will have more pumps on in a best efficiency staging approach than you would with speed-based staging. And the reason we do that is because it actually consumes less energy, just because of the shape of the efficiency curves and where they operate. So here's an example of a project that we worked on where we had 3 40 horsepower pumps consuming 30,000 $30,000 in operating costs using the speed-based staging approach. And then we switched them over to a best efficiency staging, and they were down to $20,000 in operating costs for a 34% savings in operating costs. And what's worth noting is that we did not change the pumps in this instance. We just changed the staging methodology. So we were able to provide that savings just in the staging methodology approach. Okay, our last section here is on higher operating speeds and permanent magnet motors. So we know that the industry preference for many years was the 1800 RPM 4-pole motors for HVAC pumps, mainly because of the following criteria: the noise and vibration. Certainly there were some noted reliability issues with some early 2-pole 3600 RPM pumps from roughly 30 years ago. And then that all ultimately led to shorter equipment life due to the higher operating speeds. But in today's HVAC part load world, many of these issues really don't apply anymore. For example, a 3600 RPM motor in a variable flow application would be spending most of its time at 50% load or 1800 RPM. So it would be running significantly slower than that full speed at the 3600 RPM. With today's technology, each pump size actually has an optimum speed in order for you to optimize its efficiency. So many of these smaller pump sizes, 3-inch ports or smaller, should have speeds higher than 1800 RPM. And it's worth noting that many motor manufacturers have improved their 2-pole designs, both in the induction motors as well as permanent magnet motors. In fact, we've seen in the domestic water booster industry, all of the multi-stage pumps today are almost exclusively 3600 RPM. So we often ask, why is it accepted in plumbing but not in HVAC? And as you can see, many of the industries have adopted higher speed motors. Certainly Tesla motors, their electric motors run at 13,000 RPM speed, top speed, and they're pretty much whisper quiet. We also seen with the Danfoss turbocore compressors, those running at 48,000 RPM are also very high speed, but also very quiet operation. So with this, we've also seen in the industry other pump manufacturers introducing higher speed pumps. And the benefits to using higher speed pumps include, first, as I said, optimizing the pump efficiency for lower operating costs. Also, when you run the pump faster, you're able to do the same flow rate with a smaller pump. So smaller pump sizes result in lower first costs and ultimately a smaller equipment footprint for the mechanical rooms, which are usually quite space constrained. So here is our design envelope permanent magnet motor. It includes a 4.3-inch color touchscreen, and it meets the European IE5 efficiency level. And this is basically 2 levels above NEMA Premium for an efficiency improvement of 3 to 12 percentage points at full load, and even more savings at part load. As far as the motor construction, this is a cutaway of a typical induction motor. The permanent magnet motor is very similar in construction, where you have the rotor just replaced with the instead of energizing a bar of iron with copper windings, you've replaced that with permanent magnets. And because of the higher magnetic flux, you're able to achieve a lot more with less material and operate generating much more power. Here's a look at the motor efficiency at lower speeds. So not only do you get higher efficiency at full load, but also at part load, which is really ideal for HVAC because we're generally operating in a part load scenario. As far as size comparison goes, because of the permanent magnets and their higher magnetic flux, you're able to physically reduce the size and weight of the construction. So on the right, we have our design envelope permanent magnet motor at 40 pounds, and on the left was the original induction motor with your conventional variable speed drive. Almost a third the size and weight compared to the older technology. So because the permanent magnets generate higher magnetic flux density than induction motors, you're able to use less material, you're able to generate less heat. In fact, a motor's worst enemy is heat, which ultimately leads to a shorter motor life. as well as bearing damage and more maintenance. So really what we're seeing with the permanent magnet motors is that they run quieter, they run cooler, they vibrate less, and they in turn last longer. Also, the higher stable operating speeds allows us to go to smaller pumps and thus the lower installed costs. And it's worth noting that these are all synchronous speed motors, so whether it's 3600 or 1800 RPM, they are a true 3600 RPM or 1800 RPM, not 3450 or 1750 RPM. So you do get that extra speed and no loss in slippage of the motors. And finally, here we're showing the noise levels in dBA of induction motors at 2-pole and then at 4-pole. So certainly with the 2-pole motor speeds, the fan generates a lot of the excess noise, and they would be louder than your 4-pole motors. However, with the design envelope permanent magnet motors, you can see running at 3600 RPM, twice as fast as the 1800 RPM induction motor, the noise levels are on par with the 1800 RPM noise levels. So they are very quiet, even though they're running at much higher speeds. And design envelope pumps with the PM motors right now are available up to 10 horsepower in our Tango series, which is the dual pump series, as well as vertical inline pumps and our end suction pumps with integral spring isolators. So these built-in spring isolators allow you to eliminate an inertia base. And it's our sensorless control and parallel sensorless pumping control is also available for larger applications, larger commercial pumps up to 125 horsepower in our dual arm and end suction series. And for vertical inlines, we go up to 1250 horsepower. So any large district energy cooling applications you might have, we can handle those as well. So in summary, here's the benefits of design envelope pumps we talked about today, using sensorless control to save on installation costs compared to sensored systems. And also you're taking away a lot of the headache of worrying about where to install the sensor. You can reduce capital and operating costs by considering the appropriate flow redundancy for each building type. And if you're a designer, certainly these are conversations you want to have with the building owner and what would be appropriate for them. Also look at using parallel pumping systems to go use the best efficiency staging to save on operating costs. And finally, please consider using the higher operating speeds to benefit from installed cost and operation savings. And with that, I'll turn it back over to Greg.
All right, thanks a lot, David. That was awesome. That was a lot of really great stuff. And again, I want to apologize to everyone for the little technical snafu in the beginning of this thing. Luckily, it was just me introducing the whole presentation and a little reminder of the general outline. So at this point, I'm sure a lot of you have been taking part in our presentations in the past. At this point, what we're going to do is open up a poll. We're going to just take probably 90 seconds or so, and we're going to launch a poll. So, as always, we are using this as a platform where, we can do our part during this COVID pandemic. This is part of my speech from earlier that you guys had missed out on. We want to do our part during this pandemic and really give out, essentially give money to some charities and some frontline people who are doing a major role during this whole pandemic. So every week we've been donating $500 to a local charity, and we ask that you guys not pitch in, but just help us choose who should get it. So this week and every week we try and rotate a couple different charities, get people's different thoughts. So this week we're putting out the American Lung Association, St. Jude's Children's Hospital, as well as the New York City Food Bank. So please just keep sending in your responses to this. Looks like we got about half the people voting. Everyone, we'll give it about another 20, 30 seconds or so, and we'll close out the poll. So while you guys are doing that, I guess a couple of reminders. Keep sending in the questions. There's the questions, button on this thing. So send in the questions and we'll address them all one by one. Anything that might be a bit more detailed or something, we might choose to address individually and reach out to you. And then after this whole thing is over, once we've pretty much run out of questions, or usually once we hit around 11 o'clock, the thing kind of slows down. At that point, we'll close out, and then there'll be a survey, an exit survey, where we ask if you would like to be, reached out to about this topic or any other, because we don't want to just start bothering everyone who takes part in this thing. So anyone who's interested in hearing from us, just reach out or just answer the survey, and we'll get back to you. So about 75% of you all voted. That's probably good enough for now. So we are going to close out the poll, and we are going to share it. So now you all see that looks like the New York City Food Bank definitely ran away with this one. American Lung Association did not do so well. So we will make sure to donate $500 to that charity. And again, we want to thank you all for voting there. So before anyone runs away, let's get to the best part of this whole thing, and that's the Q&A. So what I'm going to do now is make sure that my other moderators who handle the Q&A are unmuted so that they can ask the questions. Rich, are you there?
I'm
Bruce,
here.
are you there?
Yes, and I got some great questions.
All right, why don't you just fire away?
All right, so the first one is that if you had to do some work on a Tango pump, could you effectively repair it while the pump was operating?
Well, we don't recommend that. Generally, because of safety, first of all, you want to turn the power off to the pump ends before you do any work. But because of the pump ends are so lightweight, you probably could do it in under 15 minutes. So we've had people do seal changes where they've, if you've noticed, there's a clamp ring there that allows you to do any seal changes or changing out the impeller or changing out the seal, where you can just remove the clamp ring, pull the rotating assembly off, do your seal change, and then reinstall it fairly quickly. And we've timed our technicians internally at 8 minutes. And so we think your typical user out in the field could probably do it in 15. But again, as far as safety goes, you do have to turn the power off to the rotating assembly.
Okay, excellent. Do you
and if you use the split coupling design like you see in the photo there, you could just you don't even have to remove the rotating assembly. You could just access the seal right from the seal chamber port there.
Excellent, excellent. Thank you. Lou, can you see those questions?
Yes, I can. I actually have a question here. I have a question that you mentioned not having the pump flexes. How do you prevent vibration, or is that an issue?
That's a good question. So our recommended installation for any of our vertical pumps is that they do not include the flex connectors. They are rigidly mounted to the piping. And because of the weight of the overall piping, plus the weight of the pump and motor, and the weight of the piping all filled with water, it's actually the pump becomes part of the piping installation. So it's fairly small in comparison to the overall weight of the whole piping system filled with water. And that's why you don't require the flex connectors on the vertical pumps. If it was a base mounted pump, like even the one on the right there, the end sections with the integral spring isolators, for those ones, we do recommend having flex connectors, because now they're mounted to the ground and you don't want to have any vibration or water hammer or anything transferred to the rest of the building.
Okay, cool. Okay. And also, with the sensorless control, the pump is programmed to, I guess, a system curve in the factory. What happens when the system curve changes on site? Does the pump need to be reprogrammed?
It actually doesn't. So you think of it as a program map, and what you have to do in the field is, if the parameters are different, you can change the parameters. So it's like changing your start and destination. Those are the only parameters that you have to change. You don't have to remap the entire map. that map would still be applicable to the pump in the field, but you change the parameters. For example, the minimum head or the zero flow head, a lot of people do change that on site, and they lower that to get more energy savings, because they find that they're still satisfying all of the loads, and they lower that to a lower value, and they're able to save more energy. And then if, for example, the pump is overestimated and you get less system resistance in the field, you want to change your design point. You want to lower your head to the actual on-site head. You could also lower that in the field. So you change the parameters, but you don't need to reprogram the map. The map would stay the same.
Awesome, thanks.
Hey, David, a quick question for you. Are there any savings by having the VFD mounted on the pump versus, say, the wall?
Oh yeah, for sure. Having it mounted directly on the pump allows you to save on the wiring. We build that into our pump price, but certainly it's very attractive in that you're connected directly to the pump, and then a lot of times we see wiring could be 30 feet away or further, so you have to consider the wiring, the labor, the conduit costs, and then you're bringing it all the way up to the ceiling or along the ground. In many instances, that's extra cost and materials and labor for all of that wiring. And then also when you wire it directly so close to the motor, you don't have to worry about many of the reflected wave issues that you might see with other installations. So as the drive and the motor get further apart, what you might get is an effect called reflected wave voltage. So if you get more than 100 feet apart between the motor and the drive, you can get issues, and then you would require additional accessories to mitigate that type of reflected wave voltage and the damage affected that you would see with that.
Okay.
So
Thanks,
many cost savings.
Thank you.
Hey, Dave, I have a question about if you're trying to use one of these design envelope pumps with a BMS, do you need a separate control panel, or is there an overriding control panel for all of these systems?
Actually, no, you don't require a extra control panel. So these pumps are all equipped with BMS protocols. So they work off of Modbus and BACnet, and they work off both the BACnet MSTP as well as the BACnet TCP/IP. So you can do internet connections as well with that. But it does include a list of BACnet points and Modbus points, so it can communicate directly with the building's BMS, and you don't need an external control panel on top of that.
Awesome. Lou, you have another question?
I got a quick question for David.
Oh.
If you split the load between two pumps, does that effectively allow to get better turn down on the VFDs versus a VFD on a pump with twice the horsepower?
Yeah, no, that's a great question, because we know we've seen a lot of boilers, especially in heating systems in shoulder seasons, that turn down quite a lot. I think it's something like 15 to 1 or 20 to 1 times, right? So it's actually easier to go with two smaller pumps running in parallel, and then if you don't need the second pump, you're just running with the one smaller pump, and you're able to achieve a higher turn down in that sense. So using the multiple pumps operating in parallel is really ideal for higher turn downs.
Great, thank you, David.
Yeah, and another question, because that you were dealing with power, right? So what happens if we have like an unstable power supply? If the voltage is 360 instead of 460, how does that affect the pump's operation?
Okay. Yeah, that sounds like your typical under voltage issue. So we've seen in some installations, actually, especially when the pumps, we had one installation where they were installed near a subway line and there was some unstable power there. So what happens is the pumps would have a warning, and they would stop running. So they have a warning, they stop running, and then they alert the users or the building owners either through the BMS, or if you connect to the cloud, you would get a text message or an email notifying you that the pumps have stopped running, and then you would have to send an operator to go restart the issue, restart the pumps, check out what the issue is, and then restart the pumps. But yeah, under voltage or unstable voltage, undercurrent, those are typical issues that would stop the pump. Just like I think many of the VFDs out there today have the same sort of approach.
But what about, you're running it at 3,600 RPMs, right? So a lot of times when we run into voltage issues, it just derates the output of the pump. Is that something that you could kind of make up on the fly if it's only running at 20% load? It could just increase the, the pressure and stuff like that at the lower voltage?
No, it's not the voltage that dictates the speed. It's the frequency.
Right.
Yeah. So if it's a lower voltage, it would probably cause it would cause you'd lose some RPMs
Right.
typically.
Okay.
But there would be a trigger to let you know that something was off there.
Okay.
David, I have another question for David. In reference to the sensorless technology, how does that differ from just having your DP sensors in the mechanical room?
Oh, yeah, okay, very good. So that's part of the embedded control logic. So it doesn't use a DP sensor at all, but it's able to interpolate. It's a fancy term they call flow loss compensation, but basically, if you install it directly in the DP sensor in the mechanical room, you're not able to detect what the zero head flow is. Whereas with the sensorless control, you can enter that value in. So if, for example, it was 100 feet at design at the design point, if you run it in the mechanical room, if you install the DP sensor in the mechanical room, the DP sensor is going to give you 100 feet differential. Whereas with the sensorless control, you can dial that, you can just digitally enter any value you want for that, and the pump would move according to the map that it's programmed for. So instead of having 100 feet, you could lower it down to 40 feet or 30 feet, for example, and then you're going down that control curve as opposed to just going straight across in sort of like a constant pressure control curve. I hope that explains it. It's easier with little diagrams, but I'm trying to explain it verbally here.
Yeah, I just got a great question about how or what's the advantage of using Pump Manager with these parallel sensorless pumps?
Yeah, so I didn't get a chance to talk about our Pump Manager service. I think I just glanced over it very quickly, but Pump Manager is our cloud-based service. So all of these pumps are cloud connectable, and when you connect to that cloud service, it collects the data within the pump and it sends it up to the cloud, and then the cloud will do its optimization through machine learning and the AI there, and then it will come back and give you recommendations on how you can improve and optimize your performance, as well as tells you when to do your service before maybe you don't need to do maintenance after 6 months and you need to do it after 13 months, for example, because you're running it at a lower service than you normally would. So it does save you as far as maintenance goes. And could you repeat the part about the sensorless?
Well, just basically with using these parallel sensorless pumps, is there any advantages? So that's it. It was just with this style of pump with design envelope pumps, right?
Yeah. So yeah, the design envelope pumps with the Pump Manager has all of those benefits of operating cost savings, and we hear a lot of, I've heard a lot of building owners and facility managers say, I commissioned the building, we did a LEED retrofit, LEED silver or LEED gold, and after the retrofit, our building is using more energy than it was before. So that happens actually probably 50% of the time, and it's unfortunate, but that's the nature of the industry today. And Pump Manager goes a long way, in my opinion, as far as helping to diagnose the trouble spots and why you're not achieving the energy savings that you're supposed to. So, and then, a building in year 1 is not going to operate the same as it will in year 2 or year 3 or year 5 or year 10. So there will be drift. You got to maintain it, and Pump Manager gives you a lot of insights to ensure that you maintain it like you would like the operation as you would in year 1.
Absolutely, absolutely. I consider it like an evolving situation, right? With all of the different pressures and things like that in the building. So I have one more question. You did a great job discussing the motors and permanent magnet motors. I was just wondering how big are these going to be getting to? Are we going to be going beyond 10 horsepower in the near future?
Yeah, certainly. We've been talking to a lot of motor manufacturers, and when we first interviewed them, I want to say 5 or 6 years ago, it was up to 10 horsepower, and I think some other manufacturers had up to 15 horsepower. Today, we've seen many other competitors going up to 100 horsepower, and we think it's going to be pretty pervasive in the industry fairly soon. The energy savings that it offers is just tremendous, and it's been, I don't know how many years since we were on NEMA Premium. We're pretty much due for that next step, next level, and that's coming with the both permanent magnet motors as well as other motor technologies like synchronous reluctance motors and so on.
Hey,
so
Dan,
they will become more mainstream. Yeah.
Sorry, I got one more question for you over here.
All right.
We were told that a competitor of ours mentioned in a webinar last week that Sensorless technology is unreliable above 10 horsepower. Do you see any truth to that?
No, and I know which one. I think I know which other pump manufacturers talking about that. Certainly, we've had Sensorless technology for 20 years or so. These permanent magnet motors we launched about 3 years ago, but Sensorless itself, we've been selling that 20 years now, and it's been very reliable for us all the way up to the hundreds of horsepowers. It's worked very well. So the key is to understand the limitation is that it's for single zone applications, and not try to apply it to other multi-zone applications. So single zone applications, more than fine for using sensorless control, and we would say 90% of the market is single zone applications.
Great, thank you.
Yeah.
Yeah, and I'll chime in on that too. So this is Greg here. So yeah, Armstrong's been offering this for 20 years, and we've been doing this for as long as I know. So 10 years plus doing with these sensorless pumps. It's commercial applications. It's almost, I'd say, 99% of what we've been installing. It works like a charm. We can give you dozens and dozens of happy, reviews from people. So just I wanted to chime in on that. So like single zone applications. In New York we do a ton of multifamily apartment houses. So it's a perfect application for that. But to David's point, I mean anything that would be considered a single zone application, you might have TRVs or something that are closing off. Maybe David could chime in a little bit more into what single zone applications might be considered. But again, in terms of multifamily apartment housing, even commercial spaces, it's so far has never been an issue for us.
Yes. So if you've just got a single mechanical room and one loop, that's I guess in the most basic form, that's a single zone application. If you're thinking of like a distributed or a central, I don't know if there's any in the New York area, but a central pumping station where you've got multiple buildings, each with their own building loads, or where you would normally have a DP sensor at the top of the building, and you're pumping to three or four different buildings, that would be multi-zone, and so that's really the difference there. So it's the complexity of the loop. in the most basic form. But I can send a little schematic. It's usually easier to show if we need to follow up on that one.
Great, thank you.
Yeah.
And also, I'll just chime in one other thing, guys. Keep the questions rolling in. We pretty much have probably another 10 minutes where we'll stay online, but we'll keep addressing questions as long as they keep coming in. So just find that little question button on your thing, send them in, and we'll address them. And anything that we don't address, we'll address kind of on a one-on-one session.
Awesome.
I had a question come in for you. Do you have any data on magnet versus windings? Do windings fail?
That's a good question. The windings do not fail in themselves. Usually it's the bearings in a motor. That is, the bearings would typically be the most common wear item, and that's usually from the heat. But the magnets themselves, they don't they don't fail because they themselves don't really move. It already has the magnetic flux inherent in the magnet. So yeah, the magnets themselves wouldn't fail. If there was, unless there's like an EMP type of a event, then the magnets wouldn't fail.
Great. Okay. Thank you, sir.
Yeah, now I actually have a good question. How many pumps can be linked up together for a single circuit? You were saying that they work best in a single circuit, right?
In the you're referring to the
Design envelope.
Yeah, the design envelope, or do you mean parallel pumping?
Basically, with the whole design envelope design, how many pumps can you put on that single loop? That they'll work together and ramp up as needed.
Okay, yeah, we as far as having pumps in parallel, we usually recommend. It really depends on the designer, but obviously there'd be at least 2, and in some instances we see 3. But we have in other, which less common ones, we've seen up to 4 in some cases, and it really varies on how they stage them. So they aren't always running 2 at a time. We probably don't see more than 4 running at a time, because at that point the parallel pumping just isn't adding a whole lot of additional pumping. It's just more redundancy that you're providing yourself.
Right.
But 4 is kind of the industry that we've seen, and that includes North America as well as other parts of the world, as the most pumps we've seen operating in parallel.
And I guess also there was like a follow-up on the permanent magnet motor versus the windings. Do the PMMs run faster, or I should say cooler than the winding style, or is there any other benefits on that?
Yeah, they do run cooler because they do generate less heat, and a lot of that is because of the slip loss. It's just the construction of the induction motors, and they are considered asynchronous. So you have to have a power to overcome that slip before it. Sorry, it's the PM motors that have the synchronous. You have to energize it before you overcome that initial inertia of the magnets. But they do run cooler, which and because they have the higher magnetic flux, they are physically smaller, which also, if you notice, the smaller motors will generate less heat, less noise, and in turn run cooler and would last longer.
Is there any horsepower advantage for the same size motor versus the winding motor?
In terms of performance wise, no. So if it's a 5 horsepower induction motor versus a 5 horsepower permanent magnet motor, then you're getting the same performance. It's just one is almost 3 times the size, whereas the other one is a third the size. But that's how they design them. So if it's 5 horsepower, we provide equivalent performance to another 5 horsepower induction motor.
Got it. All right, Greg, I'm all done with my questions.
I'm in the same boat. I agree with that at all.
All right, yeah, so it looks like the questions have stopped rolling in. It looks like we've addressed all or at least not most of them. So if none else roll in, then we'll pretty much, I guess, close this thing out. So I guess at this point,
Actually, I got one more. I just got one more, Greg.
Go ahead.
And it's based on the warranty. Did the design envelope packages come with, or what type of warranty do they have available for them?
We've still got them on our standard pump warranty, so that's 12 months from 12 months or 18 months from when it's shipped or installed.
Okay, great.
All right. And so I guess a little summary, you know, the parallel operation, you get more turn down, lower install and operating costs, higher efficiency, smaller footprint. The permanent magnet's going to be lighter, more efficient, and a longer life. And then the Sensorless technology just could sort of so many installation headaches. You ensure that you're getting the most efficient, most accurate readings, and your system is actually working. You put that DP sensor in the wrong place, everything goes out the window. So all these advancements are really just incredible. And you know what? Some of them are things, like David said, are already 20 years old. It's just for whatever reason, the industry has gotten comfortable with older technologies. But now with Local Law 97 coming around the corner, we mention it every webinar, you know, there's going to start being a bit more of a critical eye on these sorts of things. So you're really going to want to start considering these newer technologies, these more advanced technologies. And Armstrong's really just paving the path with this stuff. So, you know, as we mentioned before, anyone wants a little one-on-one conversation and a little survey when you jump out of here, you know, just click yes that you want to be contacted. You can always reach out to us at support@rathassoc.com. That's support at RATHEASSOC.com, and we'll make sure to address anything that you want. We can get together with you and your team, a little one-on-one session. We could do a go-to-webinar, or we can meet out in a field, whatever you want to do. So with that being said, David, I guess any final thoughts on your end before we end this thing?
No, it's a pleasure being able to speak to everyone here today. Thanks for having me.
Great. All right. Thanks a lot, David. And thank you, everyone, for joining us. Thank you, Rich. Thank you, Bruce, for moderating the questions. And we look forward to seeing you guys in the next presentation, probably going to be in about 2 weeks. And the idea on that one is going to be on high-efficient boiler operation. So be keep your eyes peeled. We'll get a flyer out to you probably sometime next week. Thanks again, guys.
Don't we have a PDH coming up?
Oh, yes. Good call. Next Tuesday, this upcoming Tuesday, we do have a PDH coming up on psychometrics. Good call, Rich. So that's going to be Tuesday at 10 a.m. Psychometrics going to be presented by Klaus Haglid of BPE Equipment. It's going to be a very good one, a little bit of a 101 session, but it's going to be good for beginners to advanced, and, you know, always good to get a little bit more of, I guess, a reminder on things. So thanks again, Rich, and thank you, everyone, for joining us, and we'll see you next time.